Thank you very much. I'm honored to be invited to give this colloquium, and let me stress it is really meant for the non-specialists. So all the participants of this conference, you will not hear anything new. But of course there is the reward of having wine afterwards. Okay, so K3 surfaces and friends. So I should first say what K3 surfaces are. So let me just start with one example, and let us take the Fermat equation and think of that as a hypersurface in complex projective space, and that is an example of a K3 surface. We can make it slightly more general. Instead of taking this specific equation, we could take a general degree 4 means degree 4 equation, and we should make sure that the surface is smooth, but in general this will be the case. So that's one example where K3 surfaces occur. These are projective examples, projective manifolds. Let me give you another example. So we could start with a complex two-dimensional torus. Yeah? So a C2 by a lattice, and then any such torus has an involution which sends x goes to minus x. And then we can form the quotient of that torus by this involution. Now, what will happen is that we get 16, if you think a little bit about it, there are 16 points where x is equal to minus 6, and these are fixed points of this involution. And the result is that in the quotient, these will be singularities. So these will look essentially like that. But it is easy to replace such a singular point by a P1, and then we get a surface S here, which is a resolution, and that is again a K3 surface. And you can also see here not every such torus is of algebraic variety. So here we could also get examples of non-projective, non-algebraic K3 surfaces. So let me give you a formal definition. A K3 surface is a compact complex surface such that the following is true. First of all, there exists a nowhere vanishing holomorphic 2 form. A nowhere vanishing holomorphic 2 form, call this sigma form. It's not very readable. Secondly, there are no global holomorphic 1 form. The first condition, algebraic geometers would say, okay, the canonical bundle is trivial. So this is essentially the determinant of the cotangent bundle, and the 2 form trivializes that. And for the second condition, the algebraic geometers would say these surfaces have irregularity 0. Okay, so that's the definition of a K3 surface. And it makes sense for projective surfaces, also for non-projective surfaces, but you can also read that in algebraic geometry over other fields than the complex numbers, and that could be important for, say, arithmetic applications. This is not the original definition. Well, it's not the definition given by Andre Weil. So the definition given by Andre Weil is a K3 surface is a compact complex surface which is diffeomorphic. So if you forget the complex structure, if you just look at the differentiable structure, then it is diffeomorphic to a quartic surface, or if you want, to the Fermat quartic, because all quartic surfaces by Ehresmann's theorem are diffeomorphic. That was what the definition Andre Weil used. Weil contributed very significantly to the theory of K3 surfaces. In fact, these two are equivalent. So these are equivalent definitions. That is a non-trivial statement, and that is a statement which needs Seiberg-Witten theory. Okay? So that is the introduction to K3 surfaces. Where does the name come from? The name was given by Andre Weil from Kummer, Kodaira, and Kähler, and also in memory of the beautiful mountain K2 in the Himalaya. Some people say that working with K3 surfaces is more complicated than climbing the mountain. Personally, I would never be able to climb the mountain, but I prefer to work with the K3 surfaces. Okay, so that's that. And then let me introduce the friends of K3 surfaces. Could then have a discussion about friends and relatives. So, friends. Well, we've had that definition more or less on the blackboard in the last talk. So, definition, it's slightly different, but of course, this is essentially the contents of the last talk. An irreducible, I'll say something about notation, holomorphic, symplectic manifold, call it IHSM, is a compact complex manifold with the following properties. First of all, let me call it X. First of all, it's simply connected. The fundamental group is trivial. Oh, I should have made that number 2. X should be Kähler. It should be simply connected, and there exists, and it should be up to a scalar unique. Nowhere degenerate holomorphic 2 form. Okay? Now, these, just as it stands, in particular, the third condition has 2 major consequences. The first is that the complex dimension of these manifolds is always even, so its real dimension, the dimension is divisible by 4. It's a real manifold. And second, again, the canonical bundle, meaning the determinant of the cotangent bundle, is trivial. Okay, and in dimension 2, K3s are quite obviously examples of that. Now, I gave you examples for K3 surfaces, so I should give you examples for IHSMs. Yeah, I say IHSM, I should say that these are also known as complex hyperkähler manifolds. HK. Okay, so I should give you examples, and it's not surprising that we can get examples starting from K3 surfaces. So let me start with a K3 surface. Projective or not, it doesn't matter. And then let me take a look at unordered pairs of points on that. Unordered pairs of points are the second symmetric product. And that is something which is singular. And I can desingularize it, and then I get the second, the degree 2 Hilbert scheme. So Hilbert scheme means that I look, say, of degree n, it means I look at n tuples of points. But when points come together, I don't just take the set of points, I also look at the structure of that subscheme. So for 2 pairs, it means that 2 pairs come together, but I also remember a tangent direction. Now that is something smooth, yeah? And it is an example of an IHSM. And I can do that for the degree n Hilbert schemes. These are all examples, that goes back to Bourville. Plus, and I can do one thing, I can deform these. Now, of course, I can deform them by deforming the K3 surface. However, there is one extra complex deformation which takes me out of the set of Hilb n of K3s. Yeah? So there's a genuine extra deformation here, one direction extra. That's one example. Another example is we can start with a torus. And then we can take of that torus the m+1 Hilbert scheme, and we can map that to A by taking an n tuple of points and associating it to it the sum. That makes perfect sense because A is a group, and this makes also sense when the points come together. That's called the Hilbert-Chow-morphism. And then I can take the generalized comma, that would be pi minus 1 of 0. So this is a generalized comma variety. So the comma varieties I gave you the example are the first step, but I can generalize that to higher dimension plus deformations. Yeah, as before. Those are 2 examples, 2 series. and then two examples, sporadic examples by O'Grady of dimension 6, well 10 and 6. So we essentially know 4 examples, and what we do not know is whether these are all the examples of IHSMs or not. And I think people don't have a good guess either. Yeah, I don't think anybody sort of sticks out their neck and says, yes, these are all, or no, there are definitely others around. We just simply don't know. Okay, so these are the friends. Well, where there are friends, there are also relatives. So let me define some relatives. I mean, the name is, of course, ad hoc and debatable. And sometimes friends are closer than relatives. That's the case here. So I hope this is visible. I find this is quite difficult to, yeah, but that doesn't make sense. I'll just wipe that and then go back to that blackboard to give it a chance to dry. Okay. Let's see. Okay. So what are the relatives? These are the Calabi-Yau. Well, I want to mention Calabi-Yau varieties here. A compact Kähler manifold X is a Calabi-Yau, or some people would say a Calabi-Yau in the strict sense, if, first of all, there exists a nowhere vanishing holomorphic n form, where n is the complex dimension of X. Again, this implies that the canonical bundle is trivial. And secondly, there are no global I forms for I between 1 and the dimension of X minus 1. And now if the dimension of X is 2, then all of these things come together. So X is K3 if and only if X is IHSM, if and only if X is Calabi-Yau. But then they diverge. So irreducible holomorphic symplectic I cannot have for even dimension. I can have Calabi-Yau in dimension 3, so I should have said that. Here again I can take a quintic in P4. So this is a well-known Calabi-Yau, the quintic hypersurface, or instead of the Fermat equation, I could have taken any generic degree 5 equation. Okay. So why are these important? In some sense, these are sort of the building blocks for what's called Ricci flat manifolds. So there's a well-known decomposition theorem due to Bogomolov, which says the following: let X be a Ricci flat complex Keller manifold. So Ricci flat means that the first Chern class interpreted as a real Chern class, so in H2 with real coefficients is 0. And then there is a finite cover x tilde over x, such that x tilde is a product of, say, xi, these are IHSMs, times a product of a yj, these are Calabi-Yaus, times a torus. And if you think, if you're a differential geometer, then this here is SUN holonomy, and this here is SP2M holonomy. Okay, so these are sort of the right is, well, a lot of this conference was exactly about these class of varieties. And they indeed appear in very, very many different branches of mathematics. Let me just, this really is very, very difficult to read. Let me just mention a few. So obviously, we get them in geometry. We get them, Calabi-Yau, you think of physics, you think of string theory, so we get these things in mirror symmetry. We also have a nice story. All of this is connected, of course. Derived categories, derived geometry. They play a role here. And then there are arithmetic aspects. So arithmetic aspects could be that, say, you have this variety over the rationals, over the integers, you start counting points, and then you can ask questions about modularity, about L functions. But you could also go to other fields, and you could ask nice questions about Chow groups, cycles, motifs, etc. There's a lot going on there. And there's recently been, for example, a proof of the Tate conjecture for K3s, about supersingular K3s. So there are various aspects of mathematics where these things play a major role. Okay. Now, I want to, and that's well, I'm a geometer, so I want to talk a bit about geometry and about how to classify these objects. So I'll just wipe that in the hope of producing a slightly cleaner board. Okay. Now there is a story here which is very important, which is Hodge theory and periods. So there are two things here which come together and which are very important. So let me get back to S being a K3 surface. And then I can look at H2 of SZ. And then you can do intersection theory, or you can do cup product. So you can take two of these classes, take the cup product, you land in H4, which is H0, which is Z. So the cup product defines on that a symmetric bilinear form. So we say that the cup product equips that H2 with the structure of a lattice. And the lattice which we get here is the same for all K3 surfaces. It is 3 copies of U. So U is the lattice given by this intersection form. So 2 generators, E squared equals F squared equals 0, and E of the F is 1. And the E8 minus 1 is even, which means that x squared is always even. It is unimodular, which means the determinant of the intersection form is 1. And it is negative, and it has rank 8. And that determines this completely. So I get something of rank 22, and the signature here is 319, so 3 positive and 19 negative eigenvalues. Just clear from the description I just gave you. So there is this discrete structure. Now there is also a complex structure, and that complex structure becomes apparent when I look not at the integral cohomology, but at cohomology with complex coefficients. And then one has, because these are Kähler manifolds, what is called a Hodge decomposition. So that's a Hodge decomposition. And yeah, so what is HPQ? And that is much more general. This is the Q cohomology of X with values in omega p. So if you think in the Ram or Dolbeau, this is the cohomology which comes from P times holomorphic and Q times antiholomorphic forms. And then, as always, HPQ is complex conjugate to HQP. And yeah, so in particular, the H20 is what is generated by my 2 form, my non-zero 2 form. That generates me a line in complex cohomology. And now I have 2 structures. I have this discrete structure and I have this linear structure. And Hodge theory is about the relation between this discrete structure and this linear structure. And the amazing thing, and this is Torelli, tells us that essentially all the geometry of a K3 surface is encoded in these data. So let me try and make that precise. So definition. So if S and S prime should be K3 surfaces, and then a Hodge isometry is an isometry, meaning respecting the lattice structures from H to S Z into H2S prime Z. Let me give that a name F, such that if I look at the complexification of that, it maps H20 of S to H20 of S prime. Now there is this really remarkable theorem which comes in various versions. This is so-called weak Torelli, but the Torelli theorem says that S is isomorphic to S prime as complex surfaces if and only if there exists a Hodge isometry H2F H2SZ to H2S prime Z. Okay. Now that puts us into a good position. I should perhaps clean that. So that allows me to introduce the period domain. So let me look at the 21-dimensional projective space, which is the projective space coming from the K3 lattice, and then considered as a complex vector space. Okay? Now in that I have a period domain. These are so-called period domain, and these are all points such that x comma x is 0 and x bar is positive. So this is 21-dimensional. This is a quadratic equation. So I get a 20-dimensional quadric, and that defines an open part of this quadric. Now what I can do is, well, first of all, wait for the blackboard. So let me just get rid of this here. Let me leave that for the time being. Let's see whether I can get it better. So I want to somehow relate Hodge structures to this domain. So for this I choose what's called a marking. A marking is an identification of H2Z with the K3 lattice as a lattice. Now given such a marking, I can then do the following. I can then look at phi of H20 of S, and I can think of that as a point in projective space. And it's not difficult to figure out that this is in this period domain.
Maybe you can use the third blackboard, because on the blackboard is the third one.
Okay. The third one, well, you mean you can't read that at the moment? Not at all. Okay, we'll have to wait. It will appear, but let's just wait. Let's see whether that dries, and then.
Well, there's more, which some of them are more dry.
Yes, I know, but then it doesn't get it very clean. Okay, let's see. Okay.
One more, by the way, below. One more razor in the steps.
Okay. Kill. Okay. Okay, so let's see. I think it's beginning. So a marking is an isometry of my H2 of the surface with the abstract K3 lattice. Then I take this line, remember that's a one-dimensional complex space, I map it into the vector space associated to that, go to projective space, and then I get, and that has to be proven, but it's easy, a point in this period domain omega. And all points in omega appear in that way. That is the well-known surjectivity of the period map, which is Loyinger, Kulikov, and others. This is smaller, Valerie. I'd prefer the bigger
but
one.
We can then write it here and then I put it again away.
Okay. So marking is H2SZ isom to LK3, and that maps H20 to a point X in omega, and here all points appear. Yeah? And this is called the period point of the complex surface S together with its marking. Of course, I can choose different markings. I'll get different points in my period domain, but they differ by an orthogonal transformation of my lattice. Now, we can reinterpret Torelli, and we can say that the isomorphism classes of K3 surfaces, modular isomorphism, is the same as in one-to-one correspondence with omega divided by the orthogonal group of the lattice K3. That's fine. So you can think of that as a classification result. However, the omega is a nice manifold. This group acts very badly on this. So this has no good analytic or algebraic structure. I mean, you can do it, but it's not a good sense, a good object for an analytic or for an algebraic geometry. And it's not so surprising, because here we are really working in complex geometry. We are not in an algebraic setting, and then things tend not to be so well behaved. So, yeah, let me do that. And then, to get rid of that situation, one introduces what's called a polarization. Okay, so next point is polarizations. And what I want to do is I want to put myself now into an algebraic setting. So now I assume that all of my K3 surfaces are embedded in some projective space. And you should think of polarization as an embedding. It's technically not quite right, but what we have here is we can take the hyperplane bundle of 1 and restrict it to S, and this gives us a line bundle on S, and that has positivity properties, and the definition is a polarization, but you should think of it as embeddings, although it's technically a little bit more complicated. On S is a, in my case, I always want to assume primitive, so it's no longer, it's not a multiple of another line bundle, ample, and what I really want is big and nef. Never mind what that is, line bundle on S. Okay? Now, if I have such a polarization, so I have a line bundle, and that has a first Chern class, and call that H. And that is an element in H2SZ. Yeah? So I can look at the degree of this. So H square, and this is an even lattice, so this is always an even number. So this is 2D and it's positive, yeah? And I call this the degree of the polarization. And what you should think about it, you should think about it as the degree of this embedding. So if you intersect with a complementary dimensional projective space and count the number of points. That is the degree. Okay? Now, by relatively simple lattice theory, we can assume that for a suitable marking phi, the phi of h is of the form E plus df, where E and f span a hyperbolic plane. So these are elements, they are isotropic, and E of f is 1. So I can always assume that I'm in this position. And then, by relatively simple geometry, one can prove that the h20 is always perpendicular to such an h. So what that means is I am led to look at perp of such a vector in the K3 lattice, and now that you can easily compute. This is 2u plus Te8 minus 1 plus 1 summand generated by an element with square minus 2d. And now we have that the signature of this is 219, and I can repeat that game. I don't know what I should do. Yeah, that's not bad actually. Yeah, well, we'll bring it out again. And let me call this space, this lattice here, let me call this L2D. Yeah, this is this 219, this 121-dimensional domain. And then I can look at omega 2D. These are all points in X in P, L2D tends to C, and the same condition X, X0, X, X bar positive. And now my period points of this polarized K3 surface with a marking with this property will land in that domain. And again, every point in that domain will be the image of some suitable polarized K3 surface if polarization is understood at big enough. Okay. And now we are in a slightly different situation. One thing is much better. So this is a type 4 domain. Type 4 domain. Also, the signature is now 2 comma something. And by the way, these are homogeneous spaces. This has 2 components. Doesn't really matter for that story, but they have 2 components. And if I look at one of them, then it is the connected component of S0219 divided by its maximal compact subgroup. So from group theory here, you know this very well, these homogeneous domains. And I also can think of the following group. I can think of all elements in G of OLK3 such that H is fixed. And this has the consequence that it acts on this F2D. And then I can take F2D, which is the quotient of omega 2D, by this group, and this is now the moduli space of degree 2D polarized K3 surfaces. Okay, this is irreducible, although this has 2 connected components, but this group interchanges the 2 components, so this is irreducible. This is now a nicely behaved quasi-projective variety, It has finite, it's not just an analytic space, it's actually a quasi-projective variety. It has only finite quotient singularities, and it's a nice thing. Okay? So, that's that. And then I can try and ask, do I understand the geometry of these spaces? So if 2D is 4, then, well, we have quartic surfaces. If you count the parameters up to change of coordinates, these are 19. And that goes to F14, and it is, well, essentially surjective. So we have a concrete parametrization. If 2D is 6, then I have complete intersections of a quadric and a cubic in P4, and I can map that to F6. In each of these cases, these are dominant. So here we have explicit parameterizations. And then we say that these spaces here, the moduli spaces, are uniruled. And then various people, but in particular, Mukai produced many parameterizations.
Unirational here.
Yes, I mean, well, uniruled is also true, but unirational is better. Yeah. Mukai produced many parameterizations for degrees something up to 20, roughly speaking. Now you can ask, does that always work? Can I always parameterize by some rational family these K3 moduli spaces? And the answer is no. That's a theorem. Well, I proved that with Valerie. And Greg Sankaran, saying that these moduli spaces F2D are what is called of general type for D is bigger than 61. I mean, we can do a little bit better, but essentially that. And general type means it's the explicit, it's the contrary to explicitly parameterizable. It has many holomorphic n forms, etc., but you cannot possibly have a dominant map from some projective space onto that space. Yeah? Okay, but that's a phenomenon which happens quite regularly in algebraic geometry, that you have a series of moduli spaces. They start out being nice and parameterizable, and at some point they become general type. Okay, now I don't have much time, but I would like to briefly comment what is the analogous situation for IHCM. Okay, so what's the story there? And I don't want to give full details, full proofs. Let me just make a few remarks. So H2XZ, I can no longer use the cup product, at least not in a simple way to make that a lattice, give that the structure of a lattice. I can use the cup product and then take some nth root out of the cup product when I go to H2N, but that's another story. But however, Bourvil, Bogomolov, they gave that a lattice structure. So this is a generalization of the cup product for K3 surfaces. So that's okay. Then I said we have Torelli. Now, Torelli in the above form fails. I mean, there are examples of Debar, Namikawa. However, as Misha Verbitsky proved, one can formulate a form of Torelli using the monodromy group. So I look at families of these IHDMSMs, and then I take them and say punctured family. I look what the monodromy does on how it acts on my H2, and that generates a big group, which is called the monodromy group. And you can use that monodromy group to produce a Torelli theorem. So this was proved by Verbitsky, and the monodromy groups were very much investigated by Markman, so I also would like to put Markman's name here, but the proof of Torelli is Verbitsky. Now, using that, we can still take moduli spaces and relate them to quotients, so F, to quotients of type 4 domains by some arithmetic group. And the type 4 domain will be will have different dimensions depending on which of these 4 families we consider. But the story is, that part of the story goes through. But these can have many components. So that part of the story is different, and a PhD student of mine, Apostolov, once worked that out and gave many examples of different, where one has several components. What other things did I mention? I mentioned explicit parameterizations. Yes, that does exist, but it exists in fewer cases. So explicit parameterizations in some cases, but not so many. So one is cubic fourfolds. Then there is an example due to Debar and Voisin. There's an example due to Lehn, and Zeuger. That's Christian Lehn and Manfred Lehn, not related unless mathematically. One is a PhD student of the other. Christian is a PhD student of Manfred. And a few others, but not very many. There are also general type results. Actually, they can be proven without having the full strength of Torelli, because if you have something which lies underneath your moduli space, so if you can prove general type for the one that is underneath, then you also get general type for what lies above. So that is again GHS. We did it for some K3N case, split polarization. And there was also recently some results by Matthew Dawes for generalized comma. Yeah, we did also one of the O'Grady cases. But in any cases, there are many open problems, and also problems in a completely different direction, which I didn't touch on, say something about derived category, about cubic fourfolds. You can relate them to K3s. You can ask questions about rationality of cubic fourfolds. So a lot to do, many open problems, a lot of work to do, and thank you very much for your attention.